All right, everybody, welcome to this latest office hour that's going to be focused on the incoming strong storm in California, and in particular on what the impacts might look like in Southern California, where the primary concern is the occurrence of potentially significant debris flows in the recent wildfire zones. So this will be a significant storm for much of California from about the Bay Area southward. There could be some flooding as far north as the Bay Area and parts of the Sierra Nevada foothills as well. Doesn't look overly concerning. The flooding probably will be similar to or less than the last storm up there. But where the real concern is coastal Southern California, really from the transverse ranges westward, and in particular the places that have experienced significant wildfire activity since September. So of course I'm talking about the two major fires as well as some smaller fires that occurred in January of this year during that extraordinary wildfire episode just about a month ago. And then also what occurred back in September. Remember, there was a major wildfire outbreak in Southern California also in September of 2024. And this is still the strongest storm to occur in that part of Southern California as well since that event in September. So there are quite a lot of wildfire burn areas which are either very large and or at very high intensity and or in steep terrain and or immediately in or just above, topographically speaking, highly populated neighborhoods. Each of those individually is a risk factor for debris flows, and so there are some locations that check all of those four boxes that experience both a high intensity fire, a relatively large fire, in steep terrain close to where people live. So the antecedent risk conditions are very high. The San Gabriel Mountains, of course, as well as really the most of the transverse ranges in Southern California, are famous, or I guess you could say infamous, for debris flow risk. It is a part of the world where we know that flash floods and debris flows can occur even without antecedent wildfire burn conditions, and of course we do also know that this greatly increases the risk. I think the most dramatic and tragic recent historical example are the Montecito debris flows in January of 2018, which occurred just east of Santa Barbara following the Thomas Fire, which burned in December, and a very heavy rain event that occurred just a couple weeks later, even while the fire was still smoldering in early January. That event killed, I believe, dozens of people and caused really a tremendous amount of damage. It's always difficult to invoke specific historical events because no two weather events are the same, but there is the risk of debris flows of significant magnitude with the storm coming in later this week. And just to be clear, there will be rain between now and Thursday, but the real risk of significant life-threatening debris flows in and near recent wildfire burn areas will be later Thursday and Thursday evening. So that will be the window of concern. Excuse me. And so there is a significant degree of concern, as I mentioned, because there is the potential for very high rainfall rates in Southern California. Now, what do I mean by rainfall rates? I mean how much rain falls in a short period of time, rather than the total cumulative amount of precipitation. So rainfall in Southern California will be heavy, but nothing to write home about in a certain sense. Over a multi-day period, downtown LA will see somewhere between 1 and 3 inches, as will much of the LA basin. That's a pretty good rainstorm, but there were, I don't know how many storms that exceeded that level last year. So why is this storm so much presenting so much concern when it's not even as strong as a number of storms that occurred last winter? Well, it isn't really the total amount of precipitation that's the problem. In fact, there's almost no risk of significant river flooding. It's been so dry, and these are not that impressive of numbers precipitation-wise over a multi-day period. However, the real challenge is this storm will produce potentially very high rainfall rates during the most intense period of the storm. So the heaviest 15, 30, 60 minutes of rain could be very heavy indeed. In fact, even locally very heavy or torrential downpours, either with or without some thunderstorm activity. in Southern California. That is why there's so much concern regarding debris flows, because debris flows, unlike river floods, are not responding to lots of water falling over large areas over a longer period of time. So those hydrologic response times in watersheds can range from hours to days. If it's the Mississippi River, we're talking weeks of aggregated hydrologic activity. But debris flows can form very fast and mainly occur as a result of surface runoff, not runoff getting concentrated necessarily into rivers, creeks, and streams, but just the sheer volume of water running over the soil surface in wildfire burned or otherwise vulnerable spots. And the amount of runoff that accumulates in relatively small watersheds. So we're not talking about significant rivers or necessarily even large creeks, but we're just thinking about essentially the low areas, the culverts, the little creeks and little streams that in Southern California most of the time, and probably even up to the present, are ephemeral or mainly dry and only occasionally have any water in them at all. Those are the kinds of settings where debris flows can form very quickly over the course of just 5 or 10 minutes. It does not take a lot of time. You just need very heavy rain in a short, sharp burst. Obviously, the longer it lasts, the worse it gets. But most of the rain that caused the Montecito debris flows, for example, fell in just 15 minutes. It wasn't 12, 20 inches of rain. It was less than an inch of rain in some cases, but it fell so quickly and all at once that that was really a disastrous event. Now, again, I don't necessarily expect rainfall rates that extreme during this event, but on the other hand, it doesn't take rainfall rates as extreme as what was observed during that event in 2018 to cause big time and life-threatening and certainly potentially damaging debris flows as well as flash floods. So sometimes you can get a flash flood or a debris flow, and quite frankly, sometimes it's not totally clear which is which. There's a spectrum. Debris flows are essentially highly mobile ash and mud flows, so they have a very high water content compared to, say, a landslide, but they have a very high soil or ash material content compared to a flash flood. So these are these concrete-like slurries. They have a tremendous amount of mass. They can essentially move giant boulders and rocks and vehicles down mountainsides and through canyons, and they can blow right through people's houses and essentially move them off the foundations, and in the case of an extreme event like the Montecito debris flows, demolish them as logs and vehicle-sized boulders just batter them for a prolonged period of time. So it's pretty obvious why these are dangerous, and they move with the speed essentially of that of water running downhill. So in other words, faster than you can outrun it, and generally faster than you can even outdrive it. So there's lots of videos from past years of vehicles getting caught in these kinds of flows because people try and leave too late, and then the debris flow is faster than your ability to escape. So it is quite possible there will be preemptive evacuations ordered in Southern California, because this is the kind of event where once it begins, it's generally going to be too late to do anything about it. So there might be evacuation warnings or orders for parts of LA County in particular, particularly in several wildfire burn areas of most concern, although there could be others. In my view, the greatest areas of concern are the areas within or near the Eaton burn area, so from January, as well as the Palisades burn area, although much of the Palisades burn area remains depopulated because, quite frankly, the destruction was so vast that there are not really any permanent residents who have returned yet to that region. That's a bit of a different state in Altadena and Pasadena because the destruction was a little bit more patchwork, and there's a pretty sharp gradient between places that were devastated and places that were left largely unscathed. So people have returned to certain portions of this area, and there is going to be a very high risk of debris flows there, partly because, again, think of how steep the mountains above Altadena and Pasadena are. The San Gabriel Mountains are extremely steep mountains, and the fire did burn up into the steep part of the mountain. So all of these populated areas, both the ones that were devastated by the fire and the ones that were somewhat unscathed, are both at risk during these sorts of events. The Palisades burn area, there will likely be numerous mud flows, flash floods on the Pacific Coast Highway, but much of the area remains closed, and they'll probably close the PCH preemptively. So I'm not as worried about people personally being harmed in the Palisades burn area, just because there aren't going to be that many people there who aren't first responders anyway. But the bigger risk will probably be on the Eaton fire burn area, and then as well, other fire burn areas from earlier in the year. So talking about the bridge fire, the line fire in particular. These are areas that could see very high rainfall rates, and also, unfortunately, this will be a very warm storm. So the snow level is going to be 8,000 to 9,000 feet. That's above Big Bear for the most part, and it means that rain will fall even at places that would normally see snow. So there is a risk of debris flows even at the highest elevations of these recent wildfire burn areas. So Running Springs, all of these places that were near the fire and downstream of the fires will be at risk. Again, this will be a substantial storm as far north as the Bay Area, but really nothing that's going to be overly destructive. Some urban and small stream flooding once again. The rivers will sharply rise, but probably not flood, at least not significantly. So not too many concerns up in Northern California. Concerns are squarely focused on Southern California at the moment. This will be a much better snow producer, by the way, in the Sierra Nevada than recent storms, which have been a little bit of a bust up to lake level. This one has much colder air associated with it, and because it's focused farther south, there won't be as much of a warm surge initially. So could be some good snow locally down to 2,500 feet or so. So that's pretty low elevation-wise, but certainly up at lake level should be some good snow, especially on the back half of the storm. I just wanted to remind folks this channel is sponsored by Reask, a climate tech company that's helping other companies rethink extreme weather risk in a warming world. And I think it might be time to share my screen, so just bear with me for a moment here. It's taking me just a little bit longer here, so just give me a second to bring up what I'm trying to get on the screen. All right, here we go. Okay, now you'll see my infinite mirror, and then should see satellite imagery momentarily thereafter. Okay, so just double checking that you're seeing what I'm seeing on the screen here. Yes, that's good. So I'll bring my drawing tool up for a moment. All right, so of course, California here. A nice atmospheric river, a moist subtropical plume in this region. Again, this is not the big storm. This is mostly bringing light rain. Just an illustration that it requires more than moisture to make a storm. There's not a lot of upward vertical motion in the atmosphere in this region right now, so there's just some light rain trying to form. This will be the case into tomorrow as well. Nothing threatening, just some relatively gentle rains, prefrontal rains. Some of these will affect Southern California as well as Northern California, but again, this is just sort of, it is February, it rains sometimes in California, that's no big deal. But the bigger thing is sort of this low pressure system that's trying to develop out here. And you can kind of see the beginning of the spin starting to take form. As this intensifies, it's going to drive a much stronger cold front toward California to the east. That's going to sort of progress down the coast as we go Wednesday into Thursday, reaching Southern California right around sunset on Thursday. And here's what it looks like from the perspective of integrated vapor transport. Again, this is sort of the multiplicative product of moisture in the air, so water vapor and wind speed. So you can get really high integrated vapor transport either by having really strong winds and a modest amount of moisture, or a ton of moisture and modest winds, or some combination of the two. Right now I think it is essentially some combination of the two, and you can see this atmospheric river. The reds are showing a strong atmospheric river off the coast. This is a classic mid-latitude cyclone. Again, the low pressure system is here. You can see it pretty clearly just based on this motion. And you can see this atmospheric river does in fact make it to Southern California. So instead of being focused more along this part of California from the Bay Area northward, this one's actually focused from the Bay Area southward. So this will be a stronger storm in Southern California than in Northern California. And you can see it weakens a little bit as it goes inland, but not much. This is still quite a strong atmospheric river. And remember that the thresholds that are required to make a strong atmospheric river in Southern California are a bit lower than in the north. So these are pretty robust values given that there's a strong mountain range, a pretty tall mountain range that acts as a pretty effective catcher's mitt when you have water fluxing in this direction. It kind of hits the mountains in Southern California and a lot of it gets squeezed out. So this will be a very efficient moisture squeezing storm. And then you see it kind of, then we go away here. So what do I want to show here? I'm going to show, so this is a high resolution model for now. So stepping forward in time, so here we are right around now. Yeah, this is right around now. I mentioned there's some light rain west of the Bay Area. We'll move on shore. There could be some pockets of lower snow levels in the coastal hills. Nothing, no big deal. A few showers in Southern California. Again, no big deal. But as you go into Thursday, you can see much stronger storm, much heavier rain rate. So this suggests some pretty heavy rains possible from about the San Francisco North Bay southward. So some strong gusty winds. Nothing too damaging, but 40, 50 mile an hour gusts could bring down some tree branches up north. But the real concern as this moves southward is what this will look like in Southern California. So you can see the very heavy rain now along the Monterey coast, the Big Sur coast, as we go into Thursday morning. And this cold front progresses southward and does in fact make it all the way into Southern California and LA County southward. So this is just one model representation of how things could go, but I think it's worth emphasizing, for example, that this will be a pretty well-defined front when it comes through Southern California later in the period. And so if I go to, let's go to a different model. Let's go to the European model here. But I'll use the deterministic run since we're only a couple days out here. Again, same weak light rain pattern, but then the main cold front moving through. And look how it intensifies a little bit as it moves through Southern California. So those are some very high rainfall amounts, enhanced greatly by the transverse ranges and that catcher's mitt that I suggested. Also, note very high snow levels with temperatures prior to frontal passage that are significantly warmer than average here. Bring in another model here. Let's see what the most recent update cycle shows here. This one only goes out 12 hours. If I go back to this is a slightly older run, but every 6 hours they have one that goes out further in the future. So this is another model's representation of what the storm will look like. This is at about mid-morning on Thursday. So you can see this front has already moved through the San Francisco Bay Area, but is down at the Monterey Bay Area with some pretty nasty-looking simulated reflectivity down along the Big Sur coast. This is what's going to propagate down to the LA area in about 50 or so hours from now, so a little over 2 days, a little more than 50 hours. In any case, this model run doesn't go out farther to capture when this goes into Southern California, but I'll be taking a closer look at that tomorrow. And one thing I wanted to emphasize here is that if we go over to, let's go, this one should be good for what purposes here. If I look at the surface-based instability, what we find is that actually there will be some surface-based instability with the system. As the front moves through on Thursday, what we see is some unstable air moving over northern and central California. That's illustrated by these gray and blue colors, so convective available potential energy getting up above 500 joules per kilogram in some places. And that starts to move into Southern California. So right when the cold front is moving through, these numbers don't look, if we were in the Midwest, whoops, that's a little bit too far out. Let me go forward a little bit here. All right, this is what I'm looking for. Yes, that's what I'm looking for here. So these numbers, if we were in the Midwest in tornado season, would be nothing to write home about. But in this case, these values down in Southern California ahead of the front, they may only be in the 50 to 200 joules per kilogram range, but that's enough given frontal forcing to potentially produce some very heavy convective downpours, meaning clouds, billowing tall cumulus congestus and cumulonimbus clouds, so essentially thunderstorm or thunderstorm-like clouds that are pretty tall, and you combine that with the strong winds aloft and the moisture and the frontal forcing, that has the potential to produce some localized, very heavy downpours, and that's the concern, especially in coastal Southern California, regarding debris flows. There is a chance of thunderstorms with this event, but there could be debris flows even absent thunderstorms, given that the rainfall rates will be quite high. And the chance of isolated downpours continues actually after the cold front moves through in this convective environment. Most places will dry out, but there will be isolated but very heavy showers to follow, and those too can present a debris flow hazard as well. And just to illustrate, here's a map from the Weather Service in Los Angeles. Again, our indispensable public service that is this particular branch of NOAA. There's a few specific places that I wanted to point out. First of all, they highlighted a lot of recent burn areas on this map. This is available on social media and at weather.gov. There are a lot of fires of note. The line fire is a little bit off of this map. It's over here, just over in western San Bernardino. I'm also concerned about that. But personally, I think the biggest risk in terms of combination of steep slopes, large recently burned areas, and people living near it are probably the Eaton Scar, number one, and then the bridge or line fires, number two, and then the Palisades fire. But there are, as you note, other fires that are potentially at risk of some debris flows during this period. Also, these happen to be the areas that might see the most rainfall. 4 to 5 inches on the Eaton and Bridge and line fires burn areas. So again, these are not unprecedented rainfall amounts, but a lot of that's going to fall over the course of just 2 or 3 hours, and that is the problem. 2 inches in downtown LA, again, not a record breaker, but will definitely cause some street flooding and probably a nightmarish evening commute on Thursday. So in LA, it's not a trivial thing to talk about those nightmare commutes, and that's probably going to be one of them. But there is now a high risk of significant road flooding and debris flows in wildfire burn areas or near them, despite there being essentially no risk of river flooding. So this, again, highlighting how debris flows are a different type of hazard than ordinary flooding, and that they are responding preferentially to the rainfall rates. There are other factors, of course, as well, but they are highly responsive to very intense rainfall rates. Both the underlying geology and also the antecedent precipitation to an extent. But the number one factor that matters is usually in an area that's known to be susceptible to debris flows, which this entire region, of course, is, given the background geology. When you have a major fire and you haven't had an opportunity for vegetation regrowth, which we have not since these just occurred, and the slope is steep enough, then there are significant concerns. And again, the Weather Service in LA is now indicating a high risk of burn-scarred debris flows and only a low to moderate risk of problems elsewhere. So it doesn't mean that no one could see a flood elsewhere, but again, in terms of the big stuff, the big scary stuff potentially, that's in and near these recent wildfire burn areas specifically. All right, I'm going to go ahead and answer some questions, so you're going to see my face again. All right, here. I'm just going to go through and start looking at the questions. Thanks for your patience. The first question is from Richard. Will this be the third atmospheric river event for Northern California this rain season? Have there been other years with 3 or more recorded AR events? Was the Great California Flood of 1862 an AR event? Well, I can answer this easily. Virtually every winter sees more than 3 atmospheric river events in Northern California. In fact, if we only saw 3, we would be in a severe drought. That was essentially what happened in 2013, 2014, then in the big drought years of the 2010s, where we only got 2 to 4 atmospheric rivers in a given winter. That usually puts us in a drought. There have been a couple of very wet recent winters where the number of atmospheric rivers that occurred was in the dozens, so very high number. This winter we've seen quite a few in Northern California, especially earlier in the season, although the bigger deal is just that the ones we saw earlier in the season were just very intense and slow moving rather than being especially numerous. So they produced record-breaking precipitation back in December I think it was early December. I'm losing track. It's been a very long couple of months for many reasons. But this has been a particularly wet winter in Northern California, at least north of the Bay Area, or from the San Francisco North Bay northward. South of Interstate 80, it's been a bit of a different story, although recently conditions along parts of the Central Coast and Central California have improved. It's still far drier than average in Southern California, although this storm will help chip away at that accumulated seasonal deficit somewhat, and I suspect will probably bring Southern California finally out of the bottom-ranked driest year-to-date on record, if it hasn't already. So I think that will at least accomplish that. The question is at what cost from a debris flow perspective in the fire zones. Thank you for the kind words, Anne. There's a comment from Puma Mountain Lion 777 that we did in fact just have the warmest January on record globally, not necessarily the warmest record January on record in California. In fact, it was not. But again, this goes to show you that what happens in California is not always the same thing that's happening everywhere else at any given moment. The reverse has also been true. Many of California's record-breaking heat waves have not necessarily been associated with record-breaking global heat contemporaneously, although increasingly they have, as we just see more record-breaking heat globally in general. It has been a remarkable January in the sense that the U.S. was once again one of the coldest places in relative terms on Earth. Again, this keeps happening. There are geophysical reasons why the U.S. will often be in midwinter one of the coldest, will experience one of the largest relative cold anomalies on Earth. That's because of the geographic orientation of the Rocky Mountains and the ability for extremely cold polar air masses to dive directly southward over Canada without being modified by the Pacific Ocean. That's why California does not see that kind of weather, but the Great Plains of the U.S. often does. And it's also why you can still get snowstorms right along the beaches of the Gulf Coast. How can that possibly be if the Gulf Coast, well, the Gulf of Mexico, I'm going to continue to call it the Gulf of Mexico, is really warm. Even this time of year, the water temperatures are generally in the 70s Fahrenheit, so that's balmily warm. That's as warm as the water ever gets off the coast of Southern California, and yet New Orleans, for example, or even the beaches in Mobile, Alabama, and in the Panhandle, Florida, saw up to half a foot of snow on the beach, right immediately adjacent to water that was in the 60s and 70s Fahrenheit. How is that possible when it never snows at sea level in California, where the conditions are a lot cooler on average? Well, again, this has to do with that protective influence. Technically, if you get winds blowing from the north or the northwest in New Orleans, they're blowing over land all the way from the Arctic Ocean. Think about drawing a straight line. There's no major water body that's modifying it. It's just going to blow over cold, high plains, gradually descend the southern plains, and that air is still nearly as cold by the time it gets to Louisiana in that kind of pattern, or Texas, as it was when it was passing over the Canadian border. In California, though, we have a nice big mountain range that does the opposite. It doesn't deflect those air masses to the east and south. It actually deflects those air masses away from California, providing a barrier to the north and east between the most populated parts of California and its easternmost fringe, which is included in the Great Basin and Range region. And then, of course, immediately to our west, we have this large Pacific Ocean, which is not balmily warm by any means, but it is very large, and any air mass that comes toward California from the west has got to traverse over thousands of miles, or even from the northwest or north has got to traverse over hundreds to thousands of miles of water, and that vast body of water stores an enormous amount of energy that really modifies those cold, dry Arctic air masses that try and make a beeline for California. So that is why that's possible. But it has been an extraordinary January in the sense that we had record-breaking a foot of snow in New Orleans. I mean, that is genuinely extraordinary. At the same time, in the same month that was literally the warmest January ever recorded globally. In fact, we're talking about global mean temperature anomaly for the month of January now above 1.6 degrees centigrade above the long-term global average. That's a striking and alarming number, and it is really just illustrative of just how ridiculously warm it was in other places, because if the U.S. was extremely cold for parts of January, and the globe on average was the warmest it had ever been in recorded history in January. Just imagine how warm it was elsewhere. And indeed, there were numerous places on Earth in the northern and southern hemisphere that saw, respectively, in the northern hemisphere, record-breaking winter warmth, and in the southern hemisphere, record-breaking summer warmth, because of course it's currently summer, austral summer in the southern hemisphere. So, of course, the main reason why that's happening is human-caused climate change, even though increasingly, if you work in a federal agency, you're not allowed to use the word climate or climate change. In fact, I've already been advised that grants submitted from this point forward will almost certainly be rejected if they use the word climate in them. Think about that for a minute. And then also consider the fact that this is essentially going to mandate something that is essentially unethical in science and in public service, which is to omit information that you know to be relevant to saving lives and property and to getting to the correct answer in terms of your scientific assessments and even in your risk assessments for the American population. So just to add to the conversation that I had last week, and I would encourage folks to check out my conversation from last week, the last live session on the intrinsic value of NOAA and the National Weather Service and what we risk if we lose it. And we very much do risk losing, if not these organizations in their entirety, certainly their function as world-class institutions protecting lives and property of Americans, of course, but also others as they are today. Beyond that, this has now expanded into across agencies, really a federal government-wide word search going on, and this has expanded to include more and more and more terms beyond things like equity and diversity, but now expanding into things like climate and climate change as well. So there's now a laundry list, a very long list. There is an actual list of words that are effectively banned words that you cannot use in official communications, that cannot be used in grants, even existing grants. In fact, I now know people personally have been advised that if they want to keep their grant, they have to amend it to remove this kind of language for awards and scientific funding offers that were already extended in previous years. So, in other words, if you have a grant to study climate change, you really aren't allowed to do that anymore across multiple agencies. And it's unclear the degree to which this is official policy or unofficial policy. Quite frankly, it now seems like there is no distinction between formal and informal policy, and it seems like there are just lots of claims and assertions being made that have effectively become the law of the land, even though they are not, in fact, the law of the land. So there's a lot of mass confusion. Of course, there's lots of news about what's going on with the NIH, the National Institutes of Health, and the catastrophic level of funding cuts that have now been ordered and mandated. But this is now starting to trickle into climate and weather as well. And I know a lot of folks insisted that it wasn't going to, but let me tell you, it is here and it is already happening. And so this is why I am talking about it, because once it's truly gone, then it's too late. So this is the moment to be having these conversations today. A little bit of a tangent based on the question, but I did want to at least touch on this in this session because this is continuing to escalate. And this is going to be a huge problem. It already is a huge problem, and it's likely to become a larger one if all federal funding is contingent on giving scientifically inaccurate information and inaccurate statements and intentionally misleading statements about the way the world is and where we're headed. It is scientific malpractice to not talk about climate change in contexts where it is in fact physically relevant. It doesn't mean it's relevant in all cases everywhere, but if we're going to pretend that it doesn't exist or that it isn't important, it doesn't mean that it's not going to still be there lurking in the background or sometimes in the foreground, as the case may be, depending on the context. And so what I am concerned about, and this is in keeping with some other decisions that we've seen, for example, the unexpected release of water, for example, into Tulare Basin earlier in the month by the Army Corps of Engineers, which was effectively an order that was politically driven rather than driven in the interest of the safety and functioning of that water storage and flood control system. We're seeing places already where decisions are being made in the interest of political expediency rather than in the interest of public safety and scientific integrity. And this is putting public servants and scientists in a really difficult position because everyone I know still really wants to continue just to do their job, to do good science or to protect the public. And they are now receiving direct orders to not do that, in short. So that's what's going on right now in the weather and climate world, and we will see where this heads, but it's not heading toward a good place right now. That is for sure. All right, well, there's a comment from Petrichor Art. Petrichor, by the way, is the word for what it smells like when it just starts to rain. I really don't like it when we get these big dumps of water all at once. Well, you and a lot of other folks, I suspect. Unfortunately, a good summary of what rain will look like in a warming world is when it rains, it pours increasingly, to an increasing degree. So when it rains increasingly, it pours. How about that? And there is a lot of physics behind that. I've talked about the expanding atmospheric sponge effect, and I still actually, as soon as I say this, I'm realizing I still haven't done a dedicated live stream focused on our recent hydroclimate whiplash paper. In fact, there's now 2 papers relevant to that we've put out in the last 2 months. So whenever I get a moment and I'm not running around as if my hair is on fire constantly, which it certainly is what it's felt like recently, we'll have that conversation once the weather calms down a little bit in California. Once we get through this series of atmospheric rivers, might be a good time for that. It's coming from Bill Locke that debris flows respond to 3 thresholds: seasonal total rainfall, total event rainfall, meaning the rainfall during the individual storm or storm sequence, and the intensity of event rainfall. And then the actual numbers that are relevant, of course, vary with the substrate. So essentially the geology and the soil conditions, as well as the presence or absence of recent wildfire in the area. All of that's, of course, true. I'm really emphasizing the intensity of the rainfall event because that is the thing that will be the most anomalous during this event, as well as the preconditioning of the substrate, i.e. the fact that a lot of these areas have recently burned in wildfire. So that greatly alters the substrate in those local areas to be much more vulnerable to high rates of runoff, mobilization of debris, so both ash that can form sort of that concrete slurry, but also larger debris, the logs, the rocks that are now loose because you don't have plant root systems holding them into the soil, for example. All of that increases the risk of debris flow. So we know that the fire risk, that already happened, and that's 100% certainty. But we're also pretty certain that the rainfall intensity during this event will likely be quite high. And so that's what the big concern is here. Rather than really high event totals, it is really more the 100% certainty of substrate alteration, because we know we had the fires in these places already, and the quite high confidence of very intense hour or 30-minute rainfall rates, for example, during the storm on Thursday evening at its peak. It's a question whether this storm system could produce thunderstorms. There's a chance for thunderstorms in the Bay Area, Central California. Yes, there is definitely a chance of isolated thunderstorms from about the Bay Area southward. I think the best bet is probably south of San Francisco and from about Orange County northward. So a pretty wide swath of the Central Coast in Southern California. Again, this is notably one of the concerns about debris flows, is that even if these storms are isolated, if one of them does set up over a burn area, that is a highly likely scenario for producing a major, potentially destructive and deadly debris flow. So the problem is we can't pinpoint in advance exactly which burn areas might receive those events, if any. So if there are preemptive evacuation orders, this is a different situation than the usual kind of flood watch. If you live near a creek, you can sometimes kind of keep an eye on it. You know, if it's staying low, you're in good shape. If it's getting close to bankfull, maybe it's time to leave. This is different. Debris flows evolve over minutes, and this will likely happen after dark, so you won't see it coming. If you're in a risk zone and there are evacuation advisories, orders, or warnings, I would suggest leaving, especially because this will be a short duration event. All you got to do is leave before sunset, and you'll probably be able to come back by by sunrise in the morning. So it's just an 8 to 12 hour kind of thing in this case. So it is time limited, unlike the fires themselves, where you can be potentially evacuated almost indeterminately for days or weeks on end. This is pretty short fused. If it's going to cause problem, it's going to cause them in a relatively narrow 6 to 12 hour window, beginning Thursday afternoon, late Thursday afternoon into Thursday night. California fire season questions, we can talk about that later. There's just a little bit too much to talk about today. There's a comment from Marty, tuning in a little late, but I'm hoping you can talk a little bit about the extreme snow events in Hokkaido, Japan, in the context of what's happening on this side of the Pacific Ocean. I haven't been following too closely, but it has been a rather extraordinary sequence of events. The northernmost portions of Japan is not widely known outside of the region, but it's actually one of the snowiest places on Earth. The northern portion of Japan is actually rather far north. And again, because it is on the western side of the Pacific Ocean, it is fairly exposed to brutally cold Siberian air outbreaks that flow northwest to southeast over China and then out over the sea. And because there's relatively little water between China and Japan, comparatively speaking to the thousands of miles of water west of California, it doesn't have time to modify those Arctic air masses very much. Plus, it's at a relatively high latitude, so there's not as much sunlight. So you can get really cold air over northern Japan in winter. And the combination of the warm ocean and that very cold air aloft means that there is a combination of a lot of moisture available and atmospheric instability. So northern Japan is subject to enormous wintertime snowfalls, including Hokkaido in particular. Earlier this month, I believe it was, in February, Hokkaido, no stranger to huge, enormous snowfall totals, even at sea level, because of course the ocean is warm and the air aloft can be well below freezing, saw record-breaking snow totals. So possibly the greatest 24-hour snowfall ever observed on Earth occurred within a few days of the warmest month on record ever observed. And a lot of folks will say, well, some of this is just kind of random. We probably missed, I'm sure there have been other places on Earth that have had higher 24-hour totals and just, if a tree falls in the forest, was no one there to observe it. That's probably true, but it is true that on Hokkaido, there have been observations for well over 100 years. So it is still very notable that this region saw record-breaking snowfall. And, the science is a little bit mixed on this, but there is some evidence that the most extreme snowfalls either will not decrease in a warming climate or actually could increase. How could that be? Well, there's two competing factors. The warmer the air, the more water vapor it can hold. The same reason why flood risk and atmospheric rivers intensify in places like California in a warming climate. But also, the warmer it is, obviously, the closer you are to being on the wrong side of the freezing line, and you might get heavy rain, a heavy cold rain instead of a heavy snow if you get on the wrong side of that freezing line. But imagine, for example, a historical storm that 40, 50 years ago might have been a couple degrees below freezing. So say a 29 degree air temperature and a certain amount of moisture that brought a certain amount of snow. Say that the temperature rises by 3 degrees Fahrenheit. So it's significantly warmer. It's now 32 degrees. The water vapor holding capacity of the atmosphere increases by about, let's call it 4% per degree Fahrenheit. So you multiply 4 by 3, it's compounding, but you get close enough. 12% increase in the amount of moisture that's in the atmosphere when you're at 32 degrees as opposed to when you're at 29 degrees. Now, you're still on the right side of the freezing line. 32 degrees, it's still freezing. You're still going to get snow. But now you got 12% more moisture in the air. So you're going to get 12% more snow mass, snow water equivalent, than you did before. So the real question in a warming climate is which of these factors wins out. And on average, it's very clear, especially in most temperate regions, which were kind of marginally on the snow line, that the warming temperatures win out and it just gets too warm for snow more often than not. But there are some exceptions at very high elevations. So we talk about even in California. If we're up at like 11 or 12,000 feet, not a lot of land in California up at 11 or 12,000 feet, but there is some, we expect there to be more snow in a warming climate. Why? Well, again, it's this competing effect. Historically, it was well below freezing when it would precipitate in winter, and so you'd get snow with a lot of degrees of warming to spare. But with several degrees of warming, you're still below freezing at these elevations, but now you get 10, 20, 30% more moisture, depending on how much warming there's been, and you can get more snowfall. The same thing is true, by the way, along the shores of the Arctic Ocean. We expect to see much more snow in the Arctic, which has historically been a fairly dry place, partly because it is so cold, but as it warms, there will be more moisture in the air, and it's still going to be cold in the Arctic, still well below freezing in winter and in the shoulder seasons, and yet there'll be a lot more moisture available to precipitate as snow. So even there, where there's 10 to 15 degrees Fahrenheit of warming, here the effect is even more pronounced. Imagine if your average winter temperature in some given location in the Arctic was, 0 degrees Fahrenheit, and today it's dramatically warmer. It's 10 to 15 degrees warmer Fahrenheit in some places. Well, if your average was 0 and it's 10 degrees warmer, it's still 10 degrees Fahrenheit. It's still very cold, well sub-freezing. But now you've warmed 10 degrees Fahrenheit. 10 degrees times about 3 to 4% per degree of warming. Now all of a sudden you got 40% more moisture to work with, and you're still well below freezing. That's why the coldest places on Earth probably see a big increase in snow in a warming climate. In fact, this has been one of my favorite misunderstood arguments as to why global warming is no big deal. Arguments about how Antarctica or the Greenland ice sheet, it's snowing more than it used to. Sure, it probably is, because it's freaking cold up there. And it was so cold that it was so dry that they didn't get a lot of precipitation. But now, as temperatures rise, it's much warmer than it used to be, but you're actually getting more precipitation at warmer but still sub-freezing temperatures. So don't ever be reassured by that as a sign of the non-significance of warming temperatures on Earth. There's a bunch of other meteorological questions that are good, but I'm not going to be able to answer them in this session, just given time constraints. All right, just continuing to look down the list of comments here. Another question about what's the best weather app for your phone. The short version is I don't use one because I don't like any of them, and I remain utterly baffled that no one has created a good one. I do not understand why Apple continues to use the information that it does. It's a joke among virtually all meteorologists, who are all exceedingly frustrated with how good weather predictions have become and how bad people think they are. A divergence largely promulgated by what are sometimes described as crap apps. Most of them are just very bad, and they aren't designed with good practices when it comes to how to process raw weather model data. Another argument why it is critically important to have humans in the mix, because otherwise we automate it and we get pretty bad predictions that could have been much better had there been human interpretation of the numerical weather models. At least implement the AI correctly, folks. I mean, seriously, I don't know what's going on there. Anyway, I don't have a recommendation. I do use a radar app called Radar Scope. It's not a prediction app, but it does give you a really nice sense of precipitation that's near you. It takes some amount of knowledge to understand how to use it. It's not extremely user-friendly. It's also not that difficult to figure out. If you have an interest in weather, you can get it on your phone. I actually use the desktop version more often. It is handy to have around. If you pay for the premium plan, you get lightning data, which interestingly, is one of the few types of meteorological data, by the way, in the US that isn't just freely available from NOAA. The lightning data is one of the very few pieces of data that is mostly only available if you pay a subscription. And that is one reason why I have that. So I certainly hope we don't get to a point where all of the weather data is like that, because that would be a disaster for a lot of reasons. But I do like RadarScope, but it's not going to give you predictions about the future. Generally speaking, if I am traveling somewhere, especially internationally, my pick is usually to go to the National Meteorological Organization of whatever country I'm in, and sort of use that. I usually think that's usually a good rule of thumb. Or occasionally, if I do need to default to something commercial, I'll usually look at the Weather Channel, so weather.com. They have predictions available internationally that I think are generally better than what you get through most stock weather apps, because there actually is both there are both humans in that mix and also a slightly better automation process than we get. Again, I do not understand why the big tech providers don't just anyway, that's all. It's a story for another day. I've talked about it on Adam Conover's podcast. I've talked about it on the Slate TBD podcast. If you're interested, I've had very long conversations at length about why weather apps are not better, and what you might do if you want to get that information. In the US, of course, I personally go to weather.gov. The National Weather Service, by the way, has been prevented from creating their own app for decades due to intense lobbying pressure, due to the argument that it would be, quote, unfair to the private weather industry. I won't opine further on that, but that is factually why the National Weather Service does not have a really nice app available that's on par with the commercial apps that are out there in terms of the user interface. You can, however, at least for now, still go to weather.gov on a computer or directly on your phone and get a local forecast. And if I am traveling in the US and I'm not using my own forecasting skills, which is something, of course, that I will do on my own behalf sometimes, that is my shortcut. Weather.gov, you plug in a zip code or a town or whatever. Then the bonus is you get to read the local area forecast discussion, which is always, if you're a weather geek, it's always something that I would recommend. All right, here, a lot of comments, so I'm just going through and getting to what I can. All right, here. And I know it's tricky, folks. I really, my goal is not to talk politics either in this setting or in other settings. I don't I do engage, and I have for years, in the policy world extensively, and that is historically on a nonpartisan basis. That does not mean I do not have my own personal political opinions, of course, and that I don't have strong opinions about what's happening right now. I mean, that is just the reality. But essentially, I'm having these conversations despite my desire not to have them, because it has reached the point where it is impossible not to, even if we are just, quote unquote, sticking to the weather. Increasingly, it's really difficult to not talk about these other things too, because our ability to stick to the weather is going to be directly threatened by some of what's happening right now. And my hope is that we don't get there. But if we don't have those conversations now, and it happens, then there won't be a lot we can do about it. So I've been talking about this since late last year, and it certainly isn't going to be the focus of this channel or elsewhere. And I do appreciate it when folks keep it civil in the comments, both here in the live chat and also on the Weather West comment section. It's really just the only way I think we can all stay sane through all of this, and have these important conversations. So I understand that folks don't want to talk politics, and I don't either. I swear I don't. I don't enjoy it, but here we are. And so mostly I am sticking to the weather and the climate, of course. But where and when there are inevitable intersections with the wider world, we're going to have those conversations too. So thanks for joining me, either because of that or despite that, depending on your perspective. Yeah, I mean, folks are listing different weather apps. The reality is they're all most of them, unless they've, changed dramatically since my last assessment, middle of last year, they're all mostly deficient in the same way, in that they just take a single individual model run at one ensemble member from among dozens that are available and make that the gospel truth. Whereas really they should be doing sophisticated ensemble, either ensemble averaging at a minimum or potentially cluster analysis, which is another question that came up here. Cluster analysis is essentially taking a look at different members of the individual weather models and seeing whether there are clustered patterns within them. So as I've shown before how, for example, the European model has 51 ensemble members, each the identical or near identical mathematical model underpinning it, but each run using slightly different initial conditions. And often for the first couple of days, they're all very similar. But due to the chaos, the mathematical Lorentzian chaos of the atmosphere, those predictions diverge sometimes quite dramatically after a few days, even with infinitesimally small perturbations in those initial conditions. That's the butterfly effect at work for real. The weather apps, though, that are out there are primarily just taking one of those members and not looking at the rest, which is, again, it's a choice. It's not a choice that I would make, and it is the reason why the forecast flail around so wildly and are often wrong, less so in the short term, 1 to 3 days out, but almost always going to be flailing wildly 5, 7 days out, even 3 days out. And they're all kind of structured that way. But cluster analysis or ensemble analysis takes a look at the different members and whether there are particular clusters within them. So this can be done algorithmically using machine learning. This can be done essentially manually by skilled human meteorologists. But the basic idea of this is this: if there are 50 members, for example, of a given model, like the European weather model, and there's a pretty wide range of outcomes. Say 10 days from now, 10 of the members suggest a big storm for Los Angeles. 20 of the members suggest a kind of a weak to moderate storm, some rain but no big deal. And then another 20 model members are completely dry. That might suggest there's about 3 different clusters. So there's one cluster of outcomes that produces a pretty big storm, and they're not going to be exactly the same storm, but they're kind of similar structurally in some way, where there's something about the perturbation of initial conditions in that sense that causes a big storm in at least more than a handful of the members. But there's clearly also certain sets of perturbed initial conditions that sort of preferentially favor a weaker storm or no storm at all. So in that case, there might be a cluster of n equals 3. Or you can work backwards and define a certain number of clusters. So say you look at all the members and you say, okay, let's always divide this into 4 clusters or 5 clusters of greatest similarity and take a look at them and look at how many members fall into each cluster. And the basic analysis is this: if there are far more members in one cluster than another, that tells us that one outcome is probably more likely than the other, and we should probably favor that outcome. But if there's a more even distribution, imagine it's fully bimodal. Make it really simple and say there's 50 members and 25 of them show rain and 25 of them show no rain. Then that cluster analysis isn't that helpful in the sense that it's like, well, 50-50, rain, no rain. But oftentimes it's not 50-50. Oftentimes it'll be that there are maybe a quarter of members that are very wet and perhaps 2/3 or 3/4 are really dry. And that might tell us that, well, there's the potential for some storminess in this period, but unfortunately the most likely outcome is dry. And this is, by the way, one reason why sometimes folks on the Weather West blog will say, why do you say it's going to be so dry in the next couple of weeks? It looks like there's some significant rain in the ensemble average. Well, often that's because I've looked at each of the individual ensemble members, and of the 50, for example, 10 of them might be quite wet, but the other 40, so essentially 80% of them, are nearly dry. So in that context, being a bit agnostic about which individual model member is more reliable, because for the most part they're essentially independent and equally likely outcomes, I'm going to hedge my bets on the 80% of members that are on the drier side. Now, with the caveat that if I'm wrong, I'm going to be really wrong because it's going to be really wet if those other 10 members or 20% of model members are correct. So, interesting food for thought in terms of both your weather app and then finally answering that question about cluster analysis that I know several people have asked recently. The question from Steve quickly about the lightning data from Blitzertung, which is essentially a crowdsourced lightning data website, is certainly better than nothing. The problem is it's not a uniform global network. These are just ad hoc lightning detectors that people have, essentially radio frequency detectors in their homes, and they're just connected volunteer to a network. So these are just people's home internet connections and transmitters they've put out in their house somewhere. They're not necessarily fully reliable. The geolocations aren't always great, and of course there's no guarantee of uptime. There's spatial gaps, there's time gaps, but it's not a bad piece of information. It's an interesting network, and it is kind of a cool thing to check out. So it is an option if you don't want to or can't pay for the private lightning data. Blitzertung, I think it's blitzertung.org. It's a funny name, but I believe it's originally a German website. You can check that out. There is also some publicly available lightning data through the GLM, or the Global Lightning Mapper, which is a module on one of the most recently NOAA satellites that was launched in recent years, the geostationary satellites. So you can get some public lightning data, I should update that, in the US via the GLM and the GOES data, but it is not highly specific, so you can't pinpoint exactly where the lightning is occurring. You can kind of just get a general idea where there's lightning going on any given minute. It's still better than it used to be. Oh, there's an interesting question from Cliff. There used to be many Western region technical attachments published, and they have diminished to near zero. Do you know what's up? Well, I don't know all of the inside baseball there, and I'm sure there is some. Some of it, of course, unfortunately, is probably political, but I suspect two things have happened. And since there are often Weather Service folks who watch these live streams, you can correct me either now or later if I'm wrong. One, I think, is that, again, as usual, workloads have expanded to fill the void. So essentially, there is not much dispensation to spend a lot of time doing research. There's a lot of emergency operations and day-to-day operations, and not a lot of time for everything else because the Weather Service has been chronically understaffed and underfunded in recent years. Also, I do suspect that some of the publications that might have been internal, well, and by internal within the Weather Service, but then ultimately public documents, because it is a public resource, some of those documents that might have been written up within a weather office and published as a monograph or online back in the 90s and early 2000s are instead becoming peer-reviewed papers that are submitted to the scientific literature with or without co-authors from research or university scientific institutions. So I think that some of what was going on there might still be getting out in the form of peer-reviewed scientific papers rather than technical attachments. That would be the better outcome, I suppose. But I think it's a mix of both. It's a mix of overwork, of less value being placed on doing science in an era where there are limited resources and only so many hours in the day, only so many dollars in the budget. And also, I think a preference for when that is going to happen to submit it in a slightly more formal context to the peer-reviewed literature. I have seen several papers like that. I've even talked with some folks in the Weather Service actually about doing that with them. We haven't quite gotten to it, although I have a backlog of almost 1,000 emails I need to send people, and I'm not exaggerating. It's been a very long couple of months. So if I owe you something, I'm sorry. I'm trying my best. All right, let me see the remaining questions here before I do a quick wrap up for those who came late. All right. Well, I think that's about it for the comments today that'll be answering questions. My plan on a scheduling note, I will probably schedule another live session, haven't scheduled it yet, for late Thursday afternoon or early Thursday evening. My goal is to time it as the frontal band moves into Los Angeles. So I will be consulting my own weather models to sort of make an assessment tomorrow as to when that's most likely, and we'll schedule accordingly. I also plan to have a Weather West blog post tomorrow if I can manage to get that done on top of everything else. So that is my goal, to have a write-up tomorrow, but I will definitely have a live stream Thursday evening unless something unexpected occurs. And then I will also be able to answer questions live, showing some radar and satellite imagery as that frontal band moves in. So that always tends to be a popular type of session. Just to summarize, major storm for central and southern California, mainly on Thursday late afternoon into evening. The primary concern is the high hourly and 30-minute rainfall rates that may occur early Thursday evening, and in particular in the wildfire burn areas, both from September and from January in Southern California, where there is a high risk of significant debris flows, not just nuisance flooding or small slides, but potentially life-threatening and damaging events in and near and downstream of, so know your topography, those recent wildfire burn areas, both from January and from September. And my primary concern, given a confluence of factors, are probably the areas in and near the Eaton fire footprint, the Bridge fire footprint, and also the Line fire footprint, and as well as the Palisades fire, although again, because that area is mostly still absent people, I'm less concerned about people because for the most part, except for first responders who know how to stay out of harm's way, there aren't many people there right now at the moment. So stay tuned. I'll have a blog post tomorrow, another live stream late Thursday. If there are evacuation warnings or orders in Southern California and debris flow regions, well, that is the kind of thing that I would take pretty seriously, because you won't know that it's coming until it hits you. Debris flows are very fast, they develop quickly, and arrive largely without warning. So, and they will be occurring primarily after dark if they occur on Thursday evening. You should be mostly in the clear by sunrise Friday, so it will not be a long period of time that you would have to leave. Unless, of course, there's a major event, but then you'll be glad that you left preemptively. All right, I'll see folks later, and thank you again.